Have you ever faced one of those uh, really complex problems? You know the kind where the usual tools you have just they don't quite cut it. Maybe it's some huge data set or really knotty scientific equation, or even something in daily life that just seems to resist an exact answer. That feeling of hitting a wall. Well, what if I told you there's a breakthrough, maybe a completely new way to find exact answers to problems we once thought were, well, maybe impossible? Today, we're taking a deep dive into exactly that, a revolutionary method that's really changing how we solve high degree polynomials. It's called Ezouidi's theorem. Our mission today is to explore how this theorem gets us those precise, exact symbolic solutions, which is a really sharp contrast to the traditional ways of approximating. And to really get a feel for its power, we're going to tackle a pretty challenging example, a 14th degree polynomial.
Exactly. And the stakes here are, well, they're pretty significant. For the longest time, dealing with these really complex equations meant we had to kind of settle for estimations, numerical approximations. Ezoudi's theorem really steps onto the scene as a direct challenge to those old limits, offering a path to precision that, frankly, was thought to be unreachable before.
Okay, so let's unpack this. Imagine steering down
Yeah.
this polynomial equation going all the way up to the 14th power. Historically, what was the big roadblock? Why couldn't mathematicians just find exact solutions for these things? What were the real challenges?
Well, the core challenge has always been about precision, exactitude. Traditional methods, things like Newton's method, which many might know, they inherently give you estimations, approximations, not the actual exact values.
Right, like getting close but not quite nailing it.
Precisely. And they're prone to rounding errors. These tiny errors can build up, especially in long calculations. It's like trying to draw a perfect map with a slightly blurry photo. And what's more, for centuries, we've been working within the limitations set by, well, foundational ideas like Abel's theorem. Abel's theorem famously tells us that certain polynomials simply cannot be solved using standard algebraic operations involving roots, radicals like square roots, cube roots, that sort of thing.
Okay.
What's really groundbreaking about Ezouidi's theorem is how it confronts this head on. It sort of bypasses this limitation. It shows that even polynomials that do have radical roots can, in fact, be solved exactly,
Huh.
symbolically.
So before this theorem came along, what was the general feeling about solving these really high degree polynomials exactly? Was it just accepted that it couldn't be done?
Oh, absolutely. For decades, yeah. Many of these complex high degree polynomials were essentially put in the unsolvable box, at least in an exact symbolic sense. Mathematicians got very good at finding numerical approximations, which are incredibly useful in practice, of course, but they always lack that final, ultimate precision of a true symbolic answer.
All right, let's bring in the star of our show then. We're looking at what sounds like a real mathematical beast here.
Uh,
A 14th degree polynomial. I mean, just listing it out gives you a sense of it. Px is by 14 by 13 plus 91 by 12, 364 by 11 plus 1001 by 10, 2002 by 9 plus 3003 by 8, 3432 by 7, 3001 by 4 plus 364 by 3, 91 by 2 plus 14 by 19, 781 equals 0. Phew. So this isn't just any polynomial. It's a perfect example of the kind of problem where you'd normally say, okay, time for the numerical methods.
Exactly right. And an interesting little detail from the source material, just as an initial observation, is that for this specific polynomial, x1 is actually a root, and it's a root of multiplicity 2.
Okay, so that helps a bit. Finding one root twice.
It does. It's an important piece of information, but it doesn't fundamentally change the core challenge, which is finding all the roots exactly for such a complex equation. We still have 12 more roots to find. And this is where, if we connect it back to the bigger picture, Ezouidi's theorem really changes the game. Instead of just approximating, it gives us a framework, a method to break down the problem and solve for the roots symbolically. It does this through a structured kind of recursive process.
Mhm.
It effectively bypasses those classical limitations we talked about.
Okay, here's where it gets really interesting, this recursive process. It sounds potentially complicated itself. How does this method actually work its magic? How does it unravel something like that 14th degree monster?
Well, at its heart, the theorem works by transforming the original polynomial. It expresses it in terms of these new abstract quantities. Let's call them scary R. You can sort of think of them as maybe specialized symbolic coefficients or building blocks that are derived from the original ones. The real genius here is how these scare values are calculated. They're determined recursively, step by step, using the coefficients of the polynomial you started with. And crucially, every single one is determined symbolically. This means we maintain exact values throughout. No estimation creeps in, no rounding errors.
Ah, I see. So it keeps everything exact from the start.
Precisely. And what's truly extraordinary, almost magical, is what happens when this method is applied to our 14th degree polynomial. You'd expect maybe a complex set of these new scalar coefficients, right? But out of all the possible ones, almost all of them start at S1R all the way up to S5R, then skipping S6R, and then S7R through S12R. They all just collapse to zero.
Wow, really? They just vanish.
They just vanish through the calculation process. We're left with only two non-zero significant terms. Specifically, S6R turns out to be exactly natus 3000 times 14 to the power of 7, and S13R is exactly natus 1782 times 14 to the power of 14, all derived symbolically.
Okay, that is a dramatic simplification.
Uh-huh.
So what does knowing just those two specific non-zero scalar values actually do for us? How does that help find the roots of that intimidating polynomial?
It's the key. It means that our massive, scary-looking 14th degree polynomial, px, gets fundamentally simplified. It boils down to an equation with just three terms: px by 14 s6r by 7 plus s13r equals 0.
Just three terms for
Yeah.
that original long expression.
Three. And when we plug in those exact symbolic values we found for S6R and S13R, the equation becomes quite astonishingly. By 7.2 plus 3000 S77 AT7 by 7.1, it's 167 A2 plus by 1414 equals 0.
Ah, I see it now. If you let, say, y kills by 7, that's
Exactly. We know how to solve quadratic equations exactly. We've known that for centuries using the quadratic formula.
that's incredible. So you take this supposedly unsolvable 14th degree problem and transform it into something solvable with, well, relatively basic algebra.
That's the power of the theorem's recursive process. It restructures the problem. And from solving that quadratic for by 7, we can then find the exact values for x. This leads directly to all the exact symbolic roots, including the complex ones, often expressed using complex exponentials. It reveals the complete solution set precisely.
So this is the core differentiator then.
Yeah.
Unlike the traditional methods giving approximations, Ezouidi's theorem delivers this precise symbolic solution. Why is that precision, that exactness, such a big deal? Why should we care so much about symbolic versus approximate?
Oh, it's a huge deal. It comes down to certainty and reliability. The roots you get from this theorem are exact. They aren't fuzzy. They're not subject to the cascade of tiny errors that inevitably happen with numerical methods, especially for complex problems. You know, when you get a numerical result like x is about 1.234, there's always that about. With Ezouidi's theorem, you get the true mathematical form, maybe involving radicals or specific constants like pi or e, but it's exact. No ambiguity. This level of exactitude is absolutely critical in many fields. And, this naturally brings up the question: how can we be sure these exact, maybe complicated looking symbolic solutions are actually correct?
Yeah, good point. How
Yeah.
to check them.
Well, the source material addresses this directly. The verification process is straightforward, though potentially computationally intensive. You take each exact symbolic root that the theorem gives you, substitute it back into the original 14th degree polynomial px, and perform the symbolic calculation. If the theorem worked correctly, the result must be exactly 0. Px equals 0. This verification step is crucial, and it confirms the accuracy and power of the method.
Okay, that makes sense. So thinking beyond just this one, albeit very complex polynomial, what are the wider implications here? If this works for a 14th degree, does it work for others? Where could this lead?
The potential applicability is immense. The claim is that this method isn't just tailored for this one example. It can be applied to any high-degree polynomial, aiming to provide exact solutions without falling back on numerical approximations.
Any polynomial, that's a big claim.
It is. And think about the fields where that matters: physics, engineering, computer science, economics.
Right.
Anywhere where mathematical models demand high precision. Exact symbolic solutions are often crucial for understanding the fundamental behavior of systems, for ensuring model accuracy, for reliable predictions. Think about designing stable control systems or calculating trajectories in astrophysics or even complex optimizations in algorithms. Precision is absolutely paramount.
So it moves beyond just a theoretical curiosity.
Very much so. Getting an exact answer versus an approximation can be the difference between a successful design and a failure, or between understanding a phenomenon correctly and missing a. Oh, hey, our listener wants to join in.
Yeah,
What's up?
as you see that we already solved, let's say, 14 degree from the equation. So it's clear that we found the 14 degree from the equation. Then this theorem bypasses the limitation of a bit, and the roots are exact.
It sounds like you're picking up on a key point.
Yeah, you've definitely got the main takeaway.
What's fascinating here is that this theorem offers that exactness.
No more settling for close enough, right?
Exactly. So thinking about that quest for exact answers.
Have you ever faced one of those really complex problems?
Oh, constantly. It's part of the fun, isn't it?
You know, the kind where the usual tools you have just,
The familiar approaches just don't quite get you
they
there.
don't quite cut it. Maybe in some huge data set or a really knotty scientific equation.
Or even something in daily life that just seems to resist an exact answer.
That feeling of hitting a wall. It's frustrating.
Absolutely. But what if I told you there's a breakthrough?
Ooh, I'm intrigued. Tell me more.
Maybe a completely new way to find exact answers to problems we once thought were.
Maybe impossible. That sounds almost too good to be true.
Well, today we're taking a deep dive into exactly that.
I'm ready. Lead the way.
A revolutionary method that's really changing how we solve high degree polynomials.
And that method is?
It's called Ezouidi's theorem.
Ezouidi's theorem. Sounds important.
Our mission today is to explore how this theorem gets us those precise, exact, symbolic solutions.
Which is a really sharp contrast to the traditional ways of approximating.
Precisely. It's a whole different ballgame.
And to really get a feel for its power, we're going to tackle a pretty challenging example.
A true mathematical heavy hitter.
A 14th degree polynomial. Just the name sounds intimidating.
Exactly. And the stakes here are, well, they're pretty significant.
Significant how? Lay it on me.
For the longest time, dealing with these really complex equations meant we had to kind of settle.
Settle. I mean, compromise on the answer.
Settle for estimations, numerical approximations.
Okay, I'm following.
Ezouidi's theorem really steps onto the scene as a direct challenge to those old limits,
A challenger appears.
offering a path to precision that, frankly, was thought to be unreachable before.
So before this theorem, what were we stuck with?
Well, the core challenge has always been about precision, exactitude.
Makes sense. You want the real answer, not a stand-in.
Traditional methods, things like Newton's method, which many might know,
I've heard of that one.
they inherently give you estimations, approximations, not the actual exact values.
Right, like getting close but not quite nailing it.
Precisely. And they're prone to rounding errors.
Those pesky little inaccuracies.
These tiny errors can build up, especially in long calculations.
Like a snowball effect.
It's like trying to draw a perfect map with.
As you see in colleagues, we already solved it. We're talking from equations, unlike traditional methods, which often use numerical approximations. Here, the theorem provides a precise simple solution. This ensures that the roots we obtain here are exact and not subject to the errors that arise with numerical methods. Now that we have calculated the exact sample roots, we can, let's say, verify them by making the roots into dialects, meaning I want them to write here after alpha subscript k has to be equal and now okay. Thank you for listening and see you next time. Thank you. Bye. Thank you for listening. This is an example of 14 degree from the equation solved by the Indian research Ezouidi, and you get, let's say, now found, you get find, let's say, the 14 roots. What's needed now just put these roots inside the original form of the equation, and you'll find that it's an exact simple roots. Thank you for watching, and goodbye.